Good morning everybody. We are back with ultrafast processes. Now in the last lecture we talked about this pump probe technique. Now this pump probe technique is similar to laser flash photolysis, but only difference is that it has got faster time resolution. So this pump probe technique is basically a transient absorption technique where you generate transients by the help of lasers, laser pulses, and then you probe with a second light source. So here this is a typical example. This is your S0 state, lowest in electronic state. This is S1, next lowest, then S2 and so on. And these are the vibrational ladders, okay, and vibrational function, that is like this, and the probability is shifting to the extremes of vibration, this ladder. So what you do is, if you pump probe means you pump your, it's an electronic spectroscopy again. So you deal with electronic plus of course vibrational levels are involved, so vibronic maybe, okay. So that is you pump with a red photon, then maybe you are exciting somewhere over here. You pump with a blue photon, energy more, you are exciting at some higher energy, okay. So your system will be either over here or over here, depending on whether you are using high energy or low energy photons. So the moment it is here, then you have another pulse which is called the probe pulse, and this probe pulse is basically, as I told you that white light means you have got the option of selecting different frequencies. So you may choose different frequencies like blue, then green, then red, or in between frequencies. So that means you can probe this process, that is from here to the upper states, so that you can get information of the positions of various various levels, and also immediately after excitation what is happening, whether this is coming back to here or it is doing something else, okay. So that basically the population of the state you can monitor as a function of time, and also as a function of frequency of your probe. So various processes may happen after excitation. It is vibrational relaxation, maybe it is here, so it relaxes to the lower level. It is called the vibrational relaxation. Say from 1, 2, 3, 4, say it is excited to 5th ladder, it will come back to the lowest ladder of S1. So it is called the vibrational relaxation. Maybe intersystem crossing to S1 to say T, maybe internal conversion from S1 to S0, okay. So all these things and aspects of vibrational relaxation is pump wavelength dependence, okay. Probe wavelength dependence will also be there, and then Frank Condon factor. These are all intricate issues that we may not be able to talk more in details, okay. We can get the full spectrum of this substance of this species, or maybe we can get the kinetic traces, okay. Kinetic traces will give you the idea whether a new species is generated or a species is generated from one to another. Maybe you will be getting at one wavelength, you will be getting a decay, another wavelength you will be getting a rise, okay, like this. So with time, maybe one wavelength you will be getting decay, another wavelength you will be getting rise. So from this you can find out the mechanism. This will give you these numbers will give you the idea of what is exactly going on and at what rate this is going on, this decay process or this rise process or growth process. Okay, so that these kinetic traces are very important. So ultrafast spectroscopy, transient absorption will give you those information. So it is a very important technique. Okay, so so these are the things that we can follow. Another nonlinear optical technique is employed. Okay, is a second harmonic generation. In this process, two photons are effectively combined, that is amalgamated to form a new photon with twice of the energy, and this is called the up conversion. Although it is exactly double the energy, means it is second harmonic, but broadly it is called the up conversion, that is energy is lifted. This is typically accomplished in a strongly birefringent medium having an axis of anisotropy, like beta BBO crystal. Okay, so beta barium borate and like those. Okay, BBO crystal, okay, or maybe other crystals as well, having this geometry. Okay, so in this experiment we use in general we use thin piece of barium borate BBO to generate 400 light from 800 nanometer input. Okay, if we have say 800 nanometer, we can generate 400 nanometer light. So it is basically 2 nu 1 giving rise to nu 0, but maybe it is nu 1 plus nu 2 giving rise to another frequency which is higher than both. Okay, and that is called the up conversion, frequency up conversion. That is also another useful technique for studying this very fast processes, very fast maybe physical, maybe very fast ultra fast chemical processes. Okay. Next we will move on to another important topic, solvation dynamics. Okay, what is this solvation dynamics? Now it's a very important experiment by which we can follow this dynamics of solvation. Okay, kinetics of solvation, how solvation is going on with time. Okay, so basically you have got a sample, I mean say you have got a dye molecule. Okay, so dye molecule means it has got some absorption band. Okay, so absorption band, it absorbs at the absorption band, if you shine with light, it absorbs energy and it goes to the excited state. Now the thing is that if it happens like as follows, that you have got initial dipole moment maybe like this much. Okay, dipole moment is the product of charge and their separation. Okay, so in the excited state maybe its electron distribution changes such that dipole moment becomes more. Say initially it was like this, then it becomes like this. So dipole is changed. Okay, also it may so happen that direction of the dipole is also changed. Okay, so there is a huge change in say dipole moment between the ground state and the excited state. So then what will happen? So in the ground state, this molecule with lower dipole is solvated by solvent molecules, maybe water, maybe other polar molecules. Okay, so it remains solvated. Now, so these dipoles are oriented in a manner that it is I mean water dipoles or maybe solvent dipoles are oriented in a manner that it stabilizes the energy of the system. So it is lowest in energy. Okay, then you shine with radiation. So that means you have got this lowest level, solvated, then a level which is not at all solvated, excited. So, which is called it is your Frank Condon excited state, which is not at all solvated, and maybe dipole is increased. So, you see that here initially the molecule is there, it is solvated in a definitive fashion. Now, you excite over here. So, its energy is more and dipole may be in a reverse fashion. Okay, dipole may be in a reverse fashion. Okay, so what is going to happen for that dipole? If dipole is increased, then it is called the system has changed its polarization, state of polarization. So these dipoles will tend to reorient themselves. I mean, the solvent dipoles will tend to reorient themselves in a manner that stabilizes the system. That is, this will solve it. Okay, this will solve it. This one was originally solvated, now it will solve it. Okay, so this will solve it, and that solvation will take some time. Okay, that solvation will take some time. Why take some time? Because solvation will require, suppose your dipole is oriented this way. So, say this is your delta plus side, say this is your delta plus side. So, this delta plus side is delta plus side, this delta plus side and this delta plus side, or maybe if it is minus side, whatever, it does not really matter, means maybe this is delta plus, this is delta plus, so they will repel. Okay, same sign, it is better to say same sign. Okay, so dipole moment, its dipole is oriented this way and its dipole is oriented this way, so they will repel each other. So it will tend to reverse its orientation, that is, this arrowhead will be preferably in this side and this tail will be in the other side. So that means they are required to orient this way. That orientation takes time. Okay, that orientation takes some time. Therefore, what is going to happen? What we can observe means, if we have a efficient spectrograph, and if we can record the time dependent transients, then we should be able to find out how much time that these solvent molecules will require to stabilize the system. So what is happening, that you shine with violet light or the blue light, okay, then it is progressively stabilized, energy is stabilized. Okay, initially it is at some high energy level, and then as progressively they rotate, the overall energy changes. So this dipole is stabilized. So its energy, I mean, it is solvated. So this electronic state is solvated. Solvated means it is energetically reduced. So what is happening, that you shine with radiation, you generate this state, and then gradually you have these levels. So with time this level is stabilized. Okay. So from here to here means a little change in solvation state, another solvated state, another solvated state, another solvated state. Okay, and these are maybe all non-radiative processes. So you have got excitation, you may get emission from here to here, this is also emission, this is also emission. So now can you tell what is the difference between all these emissions? What is the difference? I guess you are right that difference is that this length is more than this length than this. So, energy gap is more here than here than here than here. So, that means corresponding frequencies will be more, I mean this way frequency will be more. Okay? Frequency will be more. So, that means your emission spectra will show a time dependent, Stokes shift. Stokes shift means its maxima, emission maxima is changing with time. Why that is changing? Because of this solvation, these levels are gradually solvated. Therefore, basically this much of Stokes shift you may observe in your emission spectra. So, if you take the emission spectra as a function of time, then surely you expect a red shift in the emission spectra, So, what do you expect? That you may expect that in the blue side means this side of your spectrum, there is a decay, and the redder side, because it is generated from here to here. So, red side you will be expecting a growth, because at t equal to 0, that is immediately after excitation, you have got only this level, this state, not this state. If you allow sufficient time or some time, then this solvated, I mean unsolvated one, or maybe this one will be transformed to this, slowly to this level. So, if you plot this intensity, or I mean fluorescence intensity as a function of time for the blue side and for the red side, you may expect there is a decay and there is a growth. Decay, why? Because this species is generated from here to here. So, therefore, it is decaying to this, and this species was not there at 0 time, that is why 0 time it is 0. Okay. So, this way you can follow the dynamics of solvation. Okay. So, that is by monitoring the time dependent fluorescence Stokes shift, you can follow the solvation, dynamics of solvation, that is the kinetics of the process. That is how this system is solvated. Okay. So, that gives you a great deal of information about the dielectric behavior, because the moment you generate a dipole, or you change a dipole of the system, then its dielectric properties is also getting affected. So, that is dielectric dependence, okay, time dependent dielectric properties that you can follow. That is how these solvent molecules are solvating. From this you can get important information about the solvent properties. Okay, what are the components of solvation? Whether this is the principal mode of solvation. I mean only rotation. Is there any translation component, or maybe some other modes by which this dipole can be solvated? So, that those informations are you can get. So, thus following this rate process, that is the rate of solvation, okay, you can follow the dielectric dependence, dielectric behavior. Okay. So, that is a very important part, and also you can follow the polarization, how this is reorienting, okay, that you can follow by measuring the polarized fluorescence. Polarized fluorescence means you follow the fluorescence, okay, fluorescence intensity at two different linearly two planes. one is perpendicular component and the another is the parallel component, and see how this is changing, okay, how this is changing with time. So, that will give you the idea of how the solvent molecules are reorienting, and also how this probe molecule is also reorienting. So, from this, by noting this polarization behavior, like you think of your polarimetry, time dependent polarimetry, okay, kind of that will give you the idea how that is changing. I mean, this solvent molecules are rotating, or this probe molecule is rotating with time. That is also another rate process. I mean, whether there is any viscous, drag force. So, that will give you the idea of viscosity that is facing by the probe molecule. Okay. So, following ultrafast processes, I mean ultrafast fluorescence, we can gather information about the micro viscosity, okay, micro viscosity of the medium. That is the viscosity that is, it is not the bulk viscosity that we do in our find out in our laboratory, okay. Oswald, using Oswald viscometer, that is a bulk viscosity, okay. Macroscopically what we it is a macroscopic one, okay. But what is in microscopic sense, that is immediately in the neighborhood of your molecule, that is dictated by the very nature of interaction of the molecule with your solvent molecule. So, that is a reporter for micro viscosity. So, you can find out that also following ultrafast spectroscopy. Okay. There is another very important thing, that is as I told you that in the last lecture, that with the advent of ultra short laser pulses, we can probe the transition state. Okay, we can probe the transition state. Now, for this, Ahmed H. Zewail in 1999, he was awarded a Nobel Prize, okay, in chemistry for his studies of the transition states of chemical reactions using femtosecond spectroscopy. Okay. I am giving you just one example, that is the sodium iodide decomposition. Now, what he has seen, that the signal what he has his group has monitored has been found to have some oscillations, okay, for the sodium iodide decomposition reaction, and that has been interpreted and has been found to be the real case from other experimental data, that it is this experiment demonstrating correctly the observation of this observation of this dissociation of sodium iodide, okay. And this dissociation, because of this dissociation, you are observing this oscillation in signal. So, how this is happening? That sodium iodide has got two potential energy surfaces. So, one is ionic, another is a covalent, and there is a crossing, okay. Now, when you excite your sample with a laser, then maybe you excite means you generate the wave packet, and that wave packet will go back and forth this way in the ionic potential energy surface. And here you see there is a close appearance of another level, that is your covalent. So, maybe what is happening, that the moment it is coming over here, it may pass from this level to this level, this covalent, and maybe it will pass out of this attractive ionic potential energy surface, okay, and giving rise to giving rise to decomposed sodium and iodine, sodium metal and iodine, okay, via the sodium iodide, some transition state. Okay. So, this has been done by ultra short laser pulses. Okay. Now, so what is this sodium iodide femtochemistry? Now, first what has been done, you see, as I told you that there is a overlap, I mean there is a crossing. So, maybe you generate your this wave packet maybe somewhere over here, which is located on the your covalent surface maybe. So, wave packet is launched on the repulsive wall of the excited surface somewhere over here. Okay. So, your sodium iodide is over here. Okay, sodium iodide is over here. Now, as the sodium iodide has been launched over here, that is wave packet, means you can think of a wave packet, you can represent your molecule in terms of a wave packet, which is a combination of various frequencies. Now, this wave packet will move back and forth over here, okay, on the ionic potential energy surface. Okay. And as it undertakes motion on this surface, it encounters the avoided crossing at 6.93 angstrom. So, here somewhere over here. Okay. So, if it passes, I mean if it encounters this point, at this point this system has got two options. Okay. One option is either it will remain over here in the attractive potential energy surface, or it will move on to this covalent, I mean this side. Okay. So, what is happening that if you record the signal, then you will be getting some oscillatory behavior. Okay. So, here it is bonded, it is the intermediate one, maybe transition state, and it is fully dissociated. Okay, fully dissociated, maybe covalent, I mean sodium dot or sodium metal and iodine atom. Okay. So, there are some fragments to fragmentation to atomic products, I mean like this, these are the atomic products, and remainder is hopping into the ionic potential surface. This is your ionic, I mean basically there is a crossing. So, this is your ionic potential surface, this is your covalent potential surface. Okay. Into the ionic potential up to the turning point, and then coming back down to start all over again. I mean it is going back and forth, so doing the same motion. So, it is moving to and fro, this motion. Okay. So, some fraction will pass to this level, I mean this surface, and some fraction will go back to your to do another round trip excursion. Okay. So, basically sodium iodide excited, it is the transition state, and then sodium plus iodine plus translational energy. So, what is happening, that signal, it is maximum, then minimum, then again maximum, then minimum. Okay. Again maximum, minimum, but you see it is gradually decreasing. Why gradually decreasing? You see maximum is decreasing, that is more of sodium iodide has passed into this repulse, I mean covalent surface. So, when it has started, okay, that is this wall, inner wall, okay, it is sodium iodide, its intensity is maximum, then some portion has passed into this giving rise to dissociation product. So, remaining will again go back to here, but with less population, therefore, its intensity will be less. Again some portion will go out, its intensity will be less. So, this way, and this minimum in the minimum in the signal corresponds to sodium plus iodide minus. So, this way with time this is decaying. Okay. So, thus through this experiment, I mean, it was for the first time demonstrated using sodium iodide, I mean using femtochemistry, that decomposition of sodium iodide to sodium and iodine occurs via an intermediate, where this intermediate is stretched a little bit, okay, and from that it is dissociated to your dissociated to sodium and iodine. Because of this, whenever it crosses over to your covalent potential energy surface, and it is a no, I mean there is no attraction, so just they will pass, I mean they will separate. Okay. So, this is the first demonstration, and if you want to know more on this, if you can go through this Ahmed Ziwail's website. You can read this Ahmed, many of his works on this topic. Okay, there are plenty of examples, okay, and details of these particular experiment. I am just giving you the overall idea, just a brief idea, that using femtochemistry, I mean using ultra short laser pulses, we can see, indeed we can follow the transition state. Okay. So, that is the usefulness of this transition state spectroscopy. It is called the transition state spectroscopy. Okay. So, it is a very useful technique by which you can probe the transition state. Okay. And here we have taken the help of these two potential energy surface, and that since they are crossing, therefore certain percentage is going out, certain percentage is just tunneling out to the covalent potential energy surface, and thereby giving rise to your your signal. So, here at 0 time maximum signal, then it is coming this way. The moment it is coming, it has got the option to pass on to this. So, certain fraction is here, again it is coming back, but with less population. I mean this wave packet is lower in height, therefore its corresponding signal will be less. Okay. So, this way the thing has been explained, and it has been found that other numbers generated from this experiment matches with whatever has been with the explanation. Okay. Now, again let us come back to nonlinear processes, because nonlinear processes are very important in especially in chemistry, nonlinear optics. Okay. So, and also nonlinear optical materials, these are of material usage. Okay. Now, this this expression has already been told earlier, that this is the polarization. This has got the first order term, second order, third order, and so on. So, you see, if it is a 2 photon process, and if the intensity is high, then 2 photon process means omega 1 and omega 2, they combine. Okay, they will combine to give you another one. Okay, this is called your frequency up conversion. Okay, 2 frequencies combine to give you another frequency. If omega 1 and omega 2, these two are same, then it is called your second harmonic generation. Okay. So, using second harmonic generation, various things can be done. Okay, but that I am not going to talk about. Suppose we have got it biphotonic absorption and followed by another probe. So, we can follow after biphotonic absorption the fate of this state. Although ordinarily with a low intensity light you cannot reach this level with sufficient population. Therefore, using lasers, and by the use of the biphotonic absorption you can follow the dynamics of the upper levels as well, which is very important. Okay, not only the ground state but upper states are sometimes very important for chemistry. Okay, maybe the moment the third photon is here, you can follow this emission from this between these two higher levels. Okay, so depending on how many photons you are using, okay, whether it is a biphotonic process or it is a monophotonic process, okay, this is very, very important. Like fluorescence subconversion, it is another technique. It is a it is like your similar to photon amalgamation. Okay, so in that case you have got your signal, I mean you have got your sample. Okay, you have got your sample. So when you shine with light, your fluorescence is coming out, you collect the fluorescence. Okay, it is collected and then it is directed to another crystal. Okay, so another crystal where a second beam is also allowed to fall on. Okay, so it is focused at that point, I mean this crystal, and because of this nonlinear effects, these two photons are combined to give you the third photon, and you monitor this third photon as a function of time. As a function of time means in the same way we did palm probe, here also similarly you generate your time axis by changing the optical path between your this excitation source and a portion of your excitation source which is fed over here, and thereby you generate the fluorescence decay curve, okay, as a function of time. So you can follow the very fast process as a function of time, that is kinetics of decay, that is ultrafast decay. Okay, so that is also very, very important. Okay, so there is another thing which is called two-dimensional electronic spectroscopy, which can study electronic structure, energy transfer dynamics, how this energy transfer is occurring with time, coupling, coherence and correlation function. So although these are not the topic of discussion, but two-dimensional electronic spectroscopy is another important topic of discussion. Okay, so in this case, excitation, I mean in 2D spectroscopy, excitation at one wavelength influences the emission at the other wavelength. Okay, and diagonal peaks, I mean this side your emission and this side is your absorption. Okay, so diagonal peaks are linear absorption and cross peaks are coupling and energy transfer. Okay, so you can follow both from 2D spectroscopy if there is any energy transfer. So this is your diagonal peak and these two are cross peaks, coupling and energy transfer, so off diagonal. Okay, so you can follow this coupling and energy transfer. Okay, so this is another, and of course with time, as a function of time, we can follow. Therefore, if you do a 2D spectroscopy, you can follow both linear absorption as also coupling and other phenomena. So this is very important. So this is, you see, this is your absorption, this is cross peaks. Oh, okay, excited state absorption, this is cross peak. This is a typical example. I mean, it is not something it is just a typical example. Okay. So, many things can be done. Okay. Excited state absorption, how this is happening, how this excited species is absorbing. Okay. So, that is important. So, let us go back. So, what we have been talking about, there is the whole thing. Let us try to sum up. Okay, that when it is ultra fast process, there are many techniques, okay, to follow. One is palm probe, another is fluorescence upconversion. These are, I mean, two parallel ways of doing ultra fast spectroscopy. Okay. And of course, if it is a multicolor experiment, that is, you pump with blue light and you want to probe with, say, red light, it is called the two color experiment. Sometimes it is a one color experiment, that is, you pump with blue and pump with red, I mean blue. Okay. So, depending on whether it is a one color experiment or two color experiment, it is named, but generally white light is used to do palm probe, and there are different experiments. As I told you, that transient absorption and fluorescence upconversion, these are very widely used techniques. And if you want to follow this solvation dynamics, one is very important way of doing is fluorescence, time resolved fluorescence, which is called the time correlated single photon counting. That is generally done maybe up to several picoseconds, means for detecting components of several picoseconds. Of course, above that, that is nanosecond also. But the moment when it is faster than several picoseconds, like say if it is below 10 picosecond, then it is difficult to follow. Then it is difficult to follow by time correlated single photon counting, TCSPC. This is another technique. Okay. So, in that case you have to use this fluorescence upconversion. Sometimes UV upconversion is also needed if the species is having a specific wavelength that the upconverted beam may not be in visible range. Okay, you may need to do UV upconversion, but the thing is that this upconversion technique, by using upconversion technique, you can follow processes, I mean very fast processes like solvation dynamics. Okay. Yet another technique, as I told you, stimulated emission is another following stimulated emission is also important. That suppose in the excited state, the species gives you stimulated emission, that is, the emission is stimulated by your excitation source. Then this kinetics of this stimulated emission gives you many more exciting informations. Okay. So, not only just following the fluorescence kinetics, stimulated emission kinetics is also very important. And most importantly, nowadays the solvation dynamics has been employed in many systems, like starting from micelles, maybe reverse micelles, maybe room temperature ionic liquid. I mean, this is a new type of solvents, green solvents. Okay. So, where I mean green chemistry starts from, I mean it is low vapor pressure, and these are called green solvents. So, chemistry in these green solvents are very interesting. So, and also if you look into the literature, you will be finding plenty of papers, plenty of observations that are reported. reported almost every day that dynamics of solvation is different in these ionic liquids compared to bulk solvents or maybe in micelles. So, study of this solvation using ultrafast fluorescence spectroscopy gives us lot many information about the very nature of the solvent and the factors that are responsible for solvating certain ion or maybe certain dipole. Okay. So, certain dipole or certain ion, how they are solvated and what are the components, whether solvent motion, cation motion or anion motion or collective other motions are important. Okay. And there are many theoretical studies also going on. So, study of solvation dynamics gives us not only just gives us the information on the dielectric polarization, but also on the behavior of this solvent molecules towards some dipole, and also this microviscosity. Okay. So, that this microviscosity can be followed by following the polarization anisotropy, that is, you do polarization experiment. Okay, like it is like you just think of this this polarimetric experiments, although it is different but similar to that. Okay. So, that's very interesting. So, ultrafast spectroscopy gives you lot many information. Okay. So, polarization kinetics gives you how these solvent molecules and this dipole is reorienting with time. Okay. So, that is also a kinetic process, that is also a time dependent time dependent process. Okay. And also most importantly, the probing of transition state. Okay. So, that and the most powerful application is the probing of transition state. Okay. And for which Professor Zewell has been awarded Nobel Prize. So, in that way it is a success of, it is one of the most important discovery that we can follow the transition state. So, spectroscopy can give you, help you, or it can help you to visualize a transition state. There are plenty of examples that you may be finding in literature about this probing of transition states. Okay. Not transition state and similar oscillatory signal that is observed not only in this sodium iodide case, but also in biological cases. Another important aspect of this ultrafast spectroscopy is that you can follow ultrafast spectroscopy means ultrafast electron diffraction or maybe X-ray diffraction can give you idea of how a ligand is migrating from one position to another. Okay. There are reports available in literature that suppose if all of you have heard of this myoglobin or hemoglobin. Okay. So, it binds carbon monoxide. Okay. Now, if we shine with ultra short laser pulses, then this carbon monoxide is detached from this iron center, and then after detachment it travels around within the protein matrix. Okay. So, how this carbon monoxide is traveling within the protein matrix. Okay, and that you can picture using the help of X-ray diffraction. Okay, that if X-ray time resolved X-ray gives you gives you the probable position of this carbon and oxygen with time. Okay, so how this is carbon monoxide is transported immediately after this flash, that you can follow. So that is another success of this ultrafast spectroscopy. So in the next piece of lecture we will take up that issue, that is take up the issue that that is ultrafast, means how ultrafast spectroscopy can be used to follow many biological processes like our vision. What is that? Means whether we can follow it using ultrafast spectroscopy, that is what is actually happening over there, what is the active molecule that is responsible over here, what is the time dependence, how it is evolving with time, okay, at what rate, whether it is very fast or it is not that much fast. Okay, so these are the questions that still remain, that is other applications, other interesting and important application of ultrafast spectroscopy, that is how these ultrafast processes can be probed. Okay, that is ultrafast processes like this sodium iodide decomposition, or maybe your carbon monoxide detachment from myoglobin. Okay, this is happening at some ultrafast time scale. So how it is, its position is changing, whether at all is changing or not, that we want to look into. So this much for today. So in the next lecture we will take up some of the remaining issues related to ultrafast spectroscopy and of course ultrafast processes. So till then, thank you.